Hello and welcome to another one of these ADD videos. I'm going to be discussing the concept of periodic motion. Whether we're talking about a pendulum or we're talking about a spring system, they're going to exhibit a periodic motion. In this case, we're going to be looking at the spring system and its oscillations back and forth, whether you compress it or elongate it, and look at the different things that we can tell from that in terms of energy, velocity, and acceleration. So this simple harmonic motion is going to play into the same thing with a pendulum. We'll discuss the differences between a physical and a simple pendulum later in a different video. Make sure you just check that one out. But for now, let's go on further with the spring system. So if we were to look at a pendulum or spring, we can describe the motion by either a sinusoidal curve that's cosine or sine, depending on where we begin our oscillation. Let's take a look at this following mass spring system. We're going to have the spring attached to a fixed end, and this mass is going to be on a frictionless surface, and it's going to be going back and forth. This x distance, the natural length of the spring, is going to be corresponding to the graph of the x-axis. That will be the 0 point. And then when we fully stretch it out or fully compress it, we're going to get the amplitude of this graph here, the sine, the A. All right? You should remember the amplitude to be the highest point or the lowest point. Just take the absolute value of this coefficient to get the amplitude. So now when we look at the trig in terms of displacement of the spring, we look at the displacement formula as a cosine function. What we saw before was just a trigonometric general review. Now, here this is more specific to our spring system or anything that undergoes simple harmonic motion. And the angular frequency is either equal to 2 pi f or the square root of the spring constant divided by its mass. This frequency is the angular frequency over 2 pi if we were to divide both sides by 2 pi there. And we know that angular frequency is also equal to the square root of km, so we can rewrite this formula in terms of frequency now. So frequency equals 1 over 2 pi square root of k over m. And if we know that the relationship between frequency and period is that they're reciprocals of each other, if you flip this thing over, you can get the period, which is the time for one fundamental cycle, 2 pi times the square root of m over k. Now, if you want to look at the relationship between velocity or displacement and velocity and acceleration, you're going to have to think of calculus. So we can also look at the velocity and acceleration as derivatives of the displacement. This is the displacement equation. If we derive it with respect to time, the derivative of cosine is a negative sine term, and you derive the inside with respect to t, and you get an omega that comes out. If that's rough for you, go back and review your trig chain rule. The derivative of the phase angle will be 0 because it's a constant. You could also take the second derivative or the derivative of the velocity, the second derivative of the displacement, to get what the acceleration is. And derivative of sine is cosine, the a omega come along for the ride, and we have to derive the inside one more time to get omega squared. Now, you could also look at these alternative formulas for acceleration of negative omega squared times x or negative km times x. Either way, you get the same thing. Okay, so now we can go and discuss some of the formulas associated with this periodic motion. There's going to be the velocity in the x direction as we're going back and forth can be obtained by taking the spring constant divided by the mass, square rooted, and then a is going to be your amplitude, m is the mass, x is going to be the position at which we're trying to find the velocity. So depending, for instance, if we want the maximal velocity, that occurs at the natural length of the spring, which, if you remember in the previous graphical discussion, that's going to be our 0. Then acceleration is going to be the negative k over m times the x, which also, if you remember from Newtonian discussions, that force equals mass times acceleration. If you divide both sides by mass, you get that acceleration equals that. Okay. Common theme is you set accelerations equal to each other to find one of those missing pieces of the puzzle. So I would bet that you would see a problem that involves that. All right, so energy we have is constant in this motion, provided there's no external forces, no friction or anything like that. And it's going to be 1/2 k amplitude squared. If they want general energy question, use this formula at the left side. If they give you a position like fully compressed or fully elongated or at the natural length of the spring, then you're going to use the right half, knowing that when it's fully compressed or fully extended, the velocity is 0. Okay, so that whole kinetic energy part of it goes to 0, and we're just in the elastic potential part of the spring. So you would plug in a negative whatever if you were compressed, and then a positive x value if you were elongated. All right, so that takes care of the formulas. Let's see what's left. Let's look at the various situations in detail. If I were to elongate the spring, the restoring force, if you remember from Hooke's law, says that it's going to be negative k delta x and opposing the elongation. And it's all going to be, this is a U, trust me, I promise you that's a U. Potential energy that's elastic in the spring, 1/2 kx squared. And this is just kind of recapping what I said earlier. However, if I compress it, then the restoring force is going to be to the right, and it's going to be kinetic energy again is equal to 0, and potential energy is 1/2 kx squared. So make sure you just practice some of these. There are more formulas associated with this that involve the angular frequency and inertia as well. I will get into that when I do some of the example videos. I don't want to bog you down with too many formulas. This is more of an introduction to periodic motion. Some of the more fundamental concepts, know that they do alter whenever you deal with inertia. And instead of having, let's say, the spring like that, let's say we have to rotate back and forth. Okay, so it could be going that way and then back that way. Okay, so now because it's rotational, we have to start dealing with, instead of frequency, we have to start dealing with angular frequency. Okay? So make sure you check out the example videos, and as always, the best way to learn this stuff or any class is to practice, practice, practice. I hope I've cleared things up for you enough to try. Thank you and have a nice day.